Hello, welcome in. We are studying compressible fluid flow subject for civil services mains, IFS and Gate Aerospace exam. So we started uh, the chapter Quasi one-dimensional flow in the last video. Now in this video we will deal with governing equations in quasi one-dimensional flow. So as quasi one-dimensional flow is just variable area flow, so consider a control volume uh, that is of variable area. Here area at inlet is A1 and area at outlet is A2, and this area is varying continuously from inlet to outlet. Okay, so first of all, continuity equation. So here uh, we are assuming that the flow is steady. So mass inflow will be equal to mass outflow. So mass inflow is your rho 1 u1 a1. Rho is density at density, the u is velocity and a is area. So at location 1 these are represented by 1. So this is the mass inflow, and here the mass outflow is rho to u2 a2. That is your equation number 1. That is your continuity equation. Okay, so that is the continuity equation for steady quasi one dimensional flow. So next is your momentum equation. So momentum equation is related to force. At location 1 there are two forces, that is one due to pressure, that is P1 into A1, and second due to momentum, that is your mass flow rate here is rho 1 u1 A1, and if you multiply by u1 then it will be uh, momentum per second or force. Okay. And at location 2 same forces are there in terms of P2 and A2, pressure force in terms of rho 2 u2 square into A2, your momentum force. In between the area is increasing continuously. If we take a small strip here, suppose here the area is increasing by an amount d, okay, and the pressure here is your P. So then the force on this strip is your P into d, okay, and this and then if we integrate it within the limit of a2 dash to a1 dash, a2 dash is area increase here and a1 dash is area increase here, or we can see like this. So this is your strip, and sorry, this is your strip within the flow, and here the pressure is your P, and here the pressure is P plus dP. So increased part is this much, so that is your dA. Okay, on dA the pressure P is acting, so P into dA. So on the strip is the on this small strip the force is P into dA, and the if we integrate it within the limit of a2 dash to a1 dash, a2 dash is increase in area here, total area increase here, and a1 dash is total increase in area here. Okay, a1 dash is here it is 0 because we are starting from here. So this is your momentum equation. Okay, so this is the momentum equation for steady quasi one dimensional flow. Note that it is not strictly an algebraic equation because of the integral term which represents the pressure force on the sides of the control volume between location 1 and 2, or we can say these are the forces on the sides of the, or on this side of the control volume, because along this the area is increasing. Okay. So this contains integral term also. Okay. This is not the same momentum equation as we have studied in one dimensional flow. So now energy equation will remain same because total energy at location 1 will be equal to total energy at location 2. So at location 1 total energy is h1 plus u1 square by 2, and at location 2 the total energy is h2 plus u2 square by 2. So because we are not adding any heat to this, we are just changing area, so it will remain constant. So, or we can say stagnation enthalpy remains constant. So this can be turned by 3 and this can be turned by 4. So these are the equations for quasi one dimensional flow. So if we put here a1 is equal to a2, then the area will not vary. Okay, so it means that the continuity equation will be rho 1 u1 is equal to rho 2 u2, and the momentum equation will be p1 plus rho u1 square is equal to p2 plus rho u2. A1 and A2 will cancel out. Okay, so these equation will be same as we have studied in quasi, sorry, one dimensional flow. This is, these are valid for quasi one dimensional flow. Okay. So now we'll deal with differential form of the equations also. Now to drive the differential forms of these equations, first of all we'll take rho UA as constant. That is your mass flow rate at any location. Okay, because of steady flow, this is constant. So if we differentiate it, then it will be d rho UA is equal to 0. So this is equation number 5 in differential flow. So we can differentiate it by using product tool also. Okay, so we'll do it later. So now for momentum equation, now consider this strip. Here the pressure is P and here the pressure is P plus dP, and density is rho, area is A, velocity U, and area here A plus dA, velocity U plus du, and density is rho plus dU. So this is your PA. Here the force is PA and momentum is rho U square A. Okay, now on this part or on this part, the pressure is P and the force is and the area is this area is du. Okay, so P into dA. Okay, so this will be in also in this direction. So now for this part, the pressure force is P plus dP into A plus dA, and the momentum force is rho plus d rho U plus du whole square into A plus dA. Okay, so this is the momentum per second here, or this is the force here. So this will be the differential form of the momentum equation. So if we drop the second order term and product of differentials, okay, then this equation can be simplified. So if we drop product of two small quantity dP and dA force or du square, okay, then and solve it, then we will get term PA here. Okay, so PA will cancel. We will get term rho U square A, rho, and if we open it, U square will get and it will also get cancelled. We will get P into dA, so P dA will also cancel. Okay, so after cancelling a term and dropping small term, we will get this equation. Okay, A dP, A U square d rho, rho U square dA, and if we solve it, we will get U square plus du square 2U du. So if we multiplied by rho, then it will be 2 rho U A du. Okay. So this will be the equation after dropping second order term. Okay. And now if we open this also, then if we differentiate it by product tool, then it will be rho U dA plus UA d rho plus A rho du, and if we multiply it by U also, then we will get this equation, rho U square dA plus rho U A du plus A U square d rho. So now if we subtract it from 6, then we will get dP is equal to minus rho U du. This is equation number 7, and this is called Euler's equation. Okay. So this is from momentum equation, and this is from continuity equation by multiplying with U, and subtracting these two, we get this Euler's equation. And energy equation is we have H plus U square by 2 is equal to constant. So if we differentiate it, it will be dH 2U du by 2, or 2 will cancel out, it will be dH plus U du is equal to 0. So this is your momentum equation. So this is your energy equation in differential form. This is the combination of momentum and continuity equation, or it is called Euler's equation. So these are the equations or the Gordon equations in quasi one dimensional